Welcome to Operations Research. Today we are going to explore one of the most powerful tools in mathematics known as the Simplex method. If you have ever wondered how massive factories decide exactly how many products to make to maximize their profit without running out of materials, you are in the right place. Let us dive in and build your understanding from the ground up. To understand how this method works, imagine you are blindfolded and dropped on the side of a large, multi-sided mountain. Your goal is to reach the absolute highest peak. Because you cannot see, you simply feel the ground and walk straight up the steepest edge you can find. When you hit a corner, you stop, find the next steepest edge going up, and walk along it. You repeat this until every single edge leading away from you goes downhill. At that moment, you know with absolute certainty you are at the summit. The Simplex method does exactly this, but with mathematics. Now that we have a mental picture, let us look at the formal definition. The Simplex method is an iterative algebraic algorithm used to solve linear programming problems. Iterative simply means it repeats a cycle of steps, getting closer to the answer each time. We use it to maximize or minimize a main goal, like profit, which we call the objective function. We must do this while following strict rules or constraints. These constraints form a geometric shape called a feasible region. The corners of this shape are our valid options, known as basic feasible solutions. The algorithm mathematically jumps from corner to corner until it finds the absolute best one. Before we can start jumping between corners, we must prepare our problem. Real-world constraints are usually inequalities, like having a maximum limit on machine hours. However, we cannot easily do algebra with inequalities. To fix this, we convert them into strict equations by adding what is called a slack variable. A slack variable simply represents the unused portion of a resource. For example, if you have a budget of $100 and spend $80, your slack is $20. Adding the slack makes the spent amount perfectly equal the limit. This brings us to the mathematical formula for our constraints. Conceptually, this equation ensures that what we use plus what we leave behind exactly equals what we have. Let us break down the symbols. X1 and X2 are our decision variables, representing the actual choices we are making, like how many chairs to build. A1 and A2 are the coefficients, showing how much resource each choice consumes. S1 is our newly added slack variable, representing the leftover resource. Finally, B1 is the total amount of that resource available. If we increase our production X, our slack S must decrease to keep the equation balanced. Now that our equations are ready, we organize them into a grid called the initial tableau and begin a strict 4-step cycle. First, we select the entering variable by finding the most negative number in the bottom row, which represents our fastest growing profit. Second, we select the leaving variable using the minimum positive ratio test to see which resource runs out first. Third, we perform a pivot operation using basic row operations to update our table to reflect our new position at a better corner. Finally, we check for optimality. If negative numbers remain in the bottom row, we repeat the cycle. If not, we have reached the summit. Let us see this cycle in action with a concrete example. A factory makes 2 products. Product 1 yields a profit of $40 and product 2 yields $30. We want to maximize our total profit, Z. The factory has 2 departments. The first department has 12 hours available and the second has 16 hours available. Product 1 takes 1 hour in department 1 and 2 hours in department 2. Product 2 takes 1 hour in both. We write our objective function for Z and our 2 inequality constraints based on the available hours. Continuing with our setup, we must convert our inequalities into equations. For the first department, we add a slack variable, S1, to represent the unused hours, making it perfectly equal to 12. For the second department, we add a second slack variable, S2 to represent its unused hours, making it equal to 16. Finally, we rewrite our objective function by moving all variables to the same side as z, giving us z minus 40x1 minus 30x2 equals 0. We now have all the pieces needed to build our initial tableau. Here, we organize our numbers into the initial tableau matrix. The columns represent our variables and the right side constants. The bottom row is our objective function. We check for optimality and see negative numbers, so we are not at the peak. We find the most negative number, negative 40, which means x1 is our entering variable. Next, we divide the right side constants by the positive numbers in the entering column. 12 divided by 1 is 12 and 16 divided by 2 is 8. The smallest positive ratio is 8, so S2 leaves. The intersection is the number 2, which is our pivot element. Moving forward, we perform our pivot operations. We divide the second row by 2 to make the pivot 1 and use it to turn the other numbers in that column to 0. This gives us our second matrix. We check the bottom row again and still see a negative number, negative 10. This means we can still make more profit by introducing x2. We calculate the ratios again. 4 divided by 0.5 is 8 and 8 divided by 0.5 is 16. The smallest ratio is 8, so S1 leaves and our new pivot element is 0.5 in the first row. We perform the pivot operations one last time, dividing the first row by 0.5 and clearing the column. We are now looking at our third and final matrix. We perform our optimality check by looking at the bottom row. The numbers are 0, 0, 20, 10 and 400. There are absolutely no negative numbers left. The algorithm is finished. Reading the rightmost column, we see x1 equals 4, x2 equals 8 and z equals 400. Physically, this means the factory should produce 4 units of product 1 and 8 units of product 2 to achieve a maximum profit of $400. This diagram visually proves what the math just did. We started at the origin, where we produced nothing and made 0 profit. In our first iteration, the algorithm saw that moving along the horizontal axis gave the fastest profit, so it jumped to the corner at 8,0, where we only made product 1. In the second iteration, it realized we could do even better by trading some of product 1 to make room for product 2, jumping to the final optimal corner at 4,8. The Simplex method literally walked the perimeter of the shade shape until it found the best spot. Now that we have seen it work, a major question is whether this algorithm will always finish. Mathematically, it is guaranteed to find the optimum in a finite number of steps, provided the problem is non-degenerate, meaning no weird ties exist where multiple corners overlap. Because there are a limited number of corners and we always move to a better one, it will never run forever. Interestingly, in the absolute worst case scenario, it has an exponential time complexity, meaning it could take an enormous amount of time. Yet, in real-world practical applications, this almost never happens, making it highly efficient for industrial optimization. Let us summarize the key takeaways from our journey. First, the Simplex method is an elegant algorithm that finds the absolute best solution by mathematically jumping from one corner of a feasible region to a better one. Second, we learned that adding slack variables is essential to convert real-world inequalities into strict equations we can solve. Third, by repeatedly updating our tableau through pivot operations, we climb the profit mountain until no negative values remain in our objective row. You have now covered the full mechanics of the Simplex method, a cornerstone of modern industrial decision-making.